Hello, Srinivas. Hello, everyone.
Good evening.
Good
Hello.
evening. Yes, if you have doubts, any doubts regarding the previous session, then please feel free to ask me. Or if you have any kind of doubt regarding this course, you can ask me. We will wait for 2 minutes for others to join. Then we will start our live session.
Hello.
Hello.
I have a doubt regarding the past session regarding the questionnaire.
Okay. Question
So
number.
can I ask?
Yes. Can you tell me the question number?
Yeah, question is the property of the block material can be improved by the process of. So the choice, most of the things are related to the, but some is the surface and some is the total. So how this question is not clear to me.
Wait. What I will do? I will project the uh, earlier session slides. Can you tell me which question it was?
No, it is not the question. It is in the assignment.
In the current for this current year assignment.
Yeah.
Actually, I am not supposed to tell the answer of the assignment questions, uh, but I can indirectly I can tell you something so that it will be helpful for you. You would be able to solve the question by yourself. Please repeat the question.
The question is the properties of bulk material can be improved by the process of
Okay.
dash. So
Yes.
in
Yes.
this, I know this is a heat treatment process.
Yes. Yes.
So there are all the options are related to this. So some is the only surface, some is the total. But the question is not clear only for the surface or total.
No, they are asking for the bulk. So definitely surface you cannot do the surface treatment for the bulk properties. So question is clear, I think. Since
Okay,
they are
then it is the bulk material is the whole property,
yes,
not
yes, yes,
the.
yes, yes, not the surface.
Okay, that is clear.
Yes,
Thank you.
yes. Okay, okay. Thank you.
Thank you.
Any other doubts, anyone? Okay. Uh, if no more doubts anyone have, then we can start this live session 2. Welcome you all to the live session 2 on the course of Fundamental of Manufacturing Processes, and course instructor is Professor D.K.T. Vedi sir, and I am Abhishek Maurya, research scholar at the IIT Madras in the Department of Mechanical Engineering. So let's start it with the first question. Please have a look on the problem and try to guess the answer, or try to just think of the answer and give your answer only in the polling session. So I have launched the poll. Please take your time and just think, and then try to give your answers in the polling section.
Casting, machining, thermal cutting.
uh, Okay. Okay, I have got few responses, and most of you are correct. So let's see the question. Best surface finish. Uh, if I will talk about the surface finish, basically it is also known as the surface texture, or sometimes it also called the surface topography. And surface finish is some qualitative term, uh, but to quantify it there are several parameters it has been used, some like lay, some surface roughness. And sometimes waviness. So these are the few parameters which are used to evaluate the surface finish uh, of the any surface of any component. So mostly if we talk about doing the manufacturing process and what we have studied till in the course, we surface finish is mostly is referred by the surface roughness. And let's see in the casting process. Here I have shown comparator. Basically it is a device uh, which shows the, it is a template for the different casting processes, what are the surface roughness value we get and how it looks like. In the industries what people do, they get the component and they try to just to compare the how the surface texture is looking like that, and based on that they just compare and they write the value, what is the roughness value is. Suppose here let's say, and these roughness values are given in the micron inches, like it, if surface roughness value is near about 900 micro inches, then it will look like this. And similarly if the surface roughness keeps on decreasing, then surface will become more smoother and smoother, and it finish will look like finish will become much better. See, if we look the 20 micro inch surface, it is very smooth compared to the this first one. So in the casting process there are many different kinds of casting, starting from the sand casting or permanent mold casting, investment casting, die casting. Based on the process we get a different range of surface roughness even in the casting process. But mostly if we see the range of surface roughness we get in the casting process lies between 10 to 70 microns. Now this is the similar kind of just a collection of the visual collections of the surface roughness or surface finish for the different conventional machining processes. Like if we see in the horizontal milling we will get surface texture something like this, and on the here we can see these are the different values of the surface roughness given in the micrometer, and for different surface roughness for different processes, horizontal milling, vertical milling, turning. So these are the typical how the surface visually looks like. We can see if roughness is more, then we can visually see that surface is not very good, finishing is not very good. So this was the this is the visually how we can say which surface is good, which surface is which surface finish is bad or poor. So typical range for the surface roughness what we get in the machining processes lies between somewhere from 0.5 to 5 micrometer. Now I will go to the thermal cutting processes. We have seen or you must have seen in the factories the components or cutting processes, the oxyacetylene cutting process you have seen in the different places. What happens, suppose we have a component like this and we try to cut into in the two parts, then we use oxyacetylene flame, and with the help of flame we try to cut the metal surface, and finally this piece get divided into two different blocks, and the kind of, but there we get very poor surface finish. What happens, melting process keeps on happening and flame keeps on moving in direction which we want to cut the material. Suppose this is material and we want to cut the whole material throughout, and this is the flame, and we will keep the flame will keep on moving in this direction, and finally this whole block get cut into the two pieces, but the surface finish which we get is poor. Typically its range is somewhere 5 to 75 micron, 0.5 to 75 micrometer. But what happens in the case of polishing? This is the visual example. This kind of components we have seen. This is the final component which we get for our use, and we can see they are very good, they have very good surface finish, they are shining, so aesthetically and functionally they are very good, and this kind of surface finish we can achieve only by the polishing or super finishing processes, and the range of roughness which we achieve is near about 0.5 to 0.1 micrometer. So this is the typical range of the surface finish value in the terms of RA. RA is a parameter which shows the average surface toughness of any surface. So these are the RA values, and we can see the abrasive polishing had the best surface finish. So out of these processes, best surface finish we can achieve from the abrasive polishing. So is it what clear to everybody, or if anyone have doubt, please let me know, I can explain again, or otherwise I will move to the next question. Okay, let's move to the next question. Please read the problem and try to solve by yourself. I will give you a minute. Meanwhile, I will create the polls. Yes, polls are live. Please try to answer your question in the polling section. Hello, Nandini. Yes, where you are facing difficulty to understand.
सर समझ नहीं आ रहा है.
ओके, आप किस ईयर के स्टूडेंट हैं?
सेकंड
ओके.
थर्ड सेमेस्टर सर.
आपने इसके पहले कोर्स के लेक्चर्स देखे हैं क्या?
नो सर, आज पहली क्लास है.
नहीं नहीं, जैसे ये तो मैं तो डायरेक्ट में ट्यूटोरियल सेशन ले रहा हूँ, पर प्रोफेसर ने जो सेशंस लिए हैं आपने उसको अटेंड किए हैं क्या?
नो सर.
ओके ओके. सो आप ना पहले उन लेक्चर्स को अटेंड कीजिए. उसमें आप अभी तक टोटल 10 लेक्चर्स अपलोड हो चुके हैं कोर्स में, तो आप उन लेक्चर्स को फ्रॉम सीक्वेंसली अटेंड करिए. आपको सब कुछ समझ में आएगा. और ये सेशन भी हम लोग रिकॉर्ड कर रहे हैं, तो आप इसको आके फिर से अटेम्प्ट करिएगा. आपको सब कुछ समझ में आएगा. आप पहले कोर्स लेक्चर को देखिए, फिर आप ये समझ जाएंगे इजली. ओके
ओके सर.
ओके.
थैंक यू सर.
ओके ओके, वेलकम. Yes, I have got the response from few of you. Okay, this time I got only one correct response. Okay, let's try to solve the question together. If you have gone through the lecture number 6, then there the title is the selection of manufacturing processes. There you must have seen this kind of graph. Basically, here the y-axis shows the melting temperature, and this x-axis shows the production volume or the number of units produced by the different processes. And here we are surrounding the here we are showing the reasons for the different kinds of manufacturing processes. This reason which I am right now highlighting, it is the reason for the machining process or the material removal processes, and this long void region is for the joining process, and this ovular region is for the deformation based process or forming process. And this hashed region is for the it is for the casting process. So let's see one by one here the first process is the machining. We can see machining is used for the materials which have low melting point, as well as it is also used for the materials which is having high melting points. But if you see the production quantity which is for which this process is suitable, it is limited to the somewhere less than 1000. So this process is not good for the very high production of volumes. So we can see there is some option, there is an option of low production rate. So for machining this will be the correct option. And let's see for the joining. This, or I should change the color. This is the area for the joining process, and based on the graph, the joining process is used for the moderate melting point material, as well as it is most preferable for the least low melting point materials. And this process is used for smaller volume also, as well as it is used for the higher volume, or let's say the mass production. So this process is also suitable for the moderate range of the volumes also, let's say here. So this is a very versatile process in the terms of the volume of the production. So if we have low production volume, if we have mass production, at the both places the joining process is suitable. But if we see for the deformation based process, which is here, this process is strictly used for the mass production only. Here if we see, if production volume is less than 1000, we cannot use these processes. If it is higher, then only we can use these forming processes. That's why deformation based processes can be used only for the high production rates, and joining process can be used for the low, moderate, as well as the high production rates. So that should be the correct match for this question. So which will be the correct answer? First C, second B, third A. Okay, this one is the correct answer for this question. So if any of you have doubt, please ask. Okay, hopefully I was clear. So let's move to the next question. Yes, yes, this question is easy if you have gone through the lecture. Please think a little and try to give your answer in the polling section. Meanwhile, I will create the polls. Yes, I have launched the polls. Okay. Yes, I have got the few responses, and yeah, two of you are correct. Let's start the solving question together. Yes, if you have studied sometime in your during your engineering curriculum that the tolerance is the acceptable range of dimensional variation that still allows for proper functioning of the component. Or I would like to show it by some diagram. Like suppose if we want to manufacture a shaft, and as per, according to the design, the dimension of shaft should be, let's say, 10 mm. But it is very difficult to manufacture a component of exact dimension. We cannot manufacture a component exactly of 10 mm. It is because of there are many factors associated with the material, machine tools, environmental situations. So there will always be some deviation in the component, in the size of the component we will get finally. But different processes have different capability uh, of producing component. Basically, they have different range of variation. Like sand casting will have different range of variation, or milling will have different. So there is a limitation for the each processes, and in bit and in between that variational deviation, that process is able to can produce the components. Let's say we wanted to produce a component of 10 mm, but finally we will suppose that a process, let's say milling. If we have given some tolerance value, like our component size should not go beyond, let's say, plus minus 0.1 mm. For this process, suppose the tolerance value for this process is specified that it is 0.1 mm. Then what we understand, if a component we are manufacturing from the milling process, if intended dimension was 10 mm, then its final dimension which we actually get, it should be remain between 10 plus minus 0.1 mm or 10.1 mm to 9.9 mm. So final component size will be lying some in between this range. So this is the meaning of the tolerance. Here is the diagram where the y-axis showing the dimensional tolerance and x-axis is showing the typical part dimension means, and these are the different processes which are listed in the based on its x-axis and y-axis, or its dimensional tolerance and typical part dimension. Suppose for example, I will explain open die forging. This is the process. It means for this process the tolerance range which we can achieve will be this region, and the this is the range. Typically this will be the range for the size of the component which we can manufacture from this open die casting. Likewise, this graph shows many processes, and let's start looking for processes which are asked in the questions. Here, sand casting. So if we look for the casting, sand casting is here, and the second process, abrasive honing. Abrasive honing is here, and third one is the plastic molding. So it was not listed in this picture, but I have added here. Best and milling. Here is the turning and milling process. And in question it is being asked the best tolerance range from which process we can achieve best tolerance range. So here y-axis is the tolerance range, and we can see the honing. Honing is the process from which we can achieve a very tight tolerances. Basically, the deviation value in the components which is produced from the honing process, there will be very little variation in its size, which was intended to get manufactured after as a final product. So it lies somewhere between 0.001 to 0.01 mm, which is very good. And from these kind of processes we get a very good surface finish, which I have earlier shown in the last figure of the first question. So correct answer will be abrasive honing. So if any one of you have doubt in this question, if not, let's move to the next question. Yes, this is a simple question. This is directly from the, I think, lecture number 8, application of the manufacturing processes. So please read it and try to answer. Meanwhile, I will create the polls. Yes, polls are live. Yes, it seems all of you know the answer. Yes, it's correct. Yes, so the let's see one by one. If you can remember, then pistons, these can be made by the casting processes, and wires, it was listed in the forming processes, and process named was drawing process. Carburetor also it can made from the casting process only. Because all these carburetors and piston, they have very tough geometry, so casting is the best route to manufacture them. And connecting rod, is made from the forging process. Yes, it has a relatively simple geometry, and connecting rods requires good strength, good mechanical properties, and we know from the forming processes we get the component which have good properties, good mechanical properties. So this is the correct answer, and this is directly from the lecture. Let's move to the next question. Yes, please read the question and think a little, and then try to answer in the polling section. Yes, polls for the question number 5 is live now. Please give your responses in the polling section. I am looking for more responses. Okay. Okay, for this question, unfortunately, I didn't receive any correct response. Okay, there is, I think, one correct response. Okay, let's discuss together. This question is mainly from the uh, strengthening of the metallic materials. Like there are several processes of the metal strengthening. So if all of you have gone through the lectures, then work hardening was work hardening, and second method was transformation hardening. Third one was the grain refinement. And last one was the precipitation hardening. So all are the processes. These are used for improving the mechanical property of the metallic materials. So mechanical property means strength of the metallic material. And out of these, this question is from the precipitation hardening. So this kind of this method is used for the improving the properties of the material. or mostly it is used for the alloys, because if we have some alloy material, if material is as it is, like whole material is in the form of alloy, or it is in the form of matrix, then it has relatively low strength. So there is a process which is called the precipitation hardening, which will be explained later in this course. Basically what happens, uh, we do some thermal treatment or heat treatment in the material, and we leave it for some time. Then what happens, some small precipitate formation starts happening inside the matrix, and these precipitates have good strength. These precipitates have good strength, and because they have good strength, then the whole material strength of the whole material increases because of presence of these precipitates. So what is the reversion? Reversion reversion is a process. Basically what happens in the reversion process, when we heat this material, this material have alloy material as well as the precipitates, and when we heat, or we are doing some uh, process on the material which requires heating, then what happens, this precipitates starts dissolving inside the matrix alloy, and when these precipitate dissolves, then what happens, the strength of the whole component again decreases. Strength decreases, and this process is called the reversion, and it happens only because of heating the material. This kind of example mostly sir has also explained in his lectures, like earlier we had alloy, and we try to weld these two. Here we try to weld these two components, and during the welding process the material near the joint gets melted, and there is a, because of heating, the precipitates inside the material dissolve, and these resins become weaker. So the material near the joint, this is the joint region, and because of the heating, this the region near the joint becomes weaker because of this reversion process. So let's see what is the correct answer for this question. First thing, because of reversion process, strength is going to decrease. So which option is there? Increase in hardness. And we know strength and hardness they are kind of proportional to each other. If strength is high, then hardness will also be high. So reversion process basically decreases strength as well as the hardness. The first option is increases hardness, so it will not be the correct answer. Decreases the hardness due to the formation of precipitates. So this is correct, decrease in hardness, but it will not happen because of formation of precipitate. This is wrong, so this option is wrong. Next is decreases the strength due to dissolution of the precipitates. Yes, this is the correct. Strength is decreases, and the reason is because of precipitates got dissolved. And last option is decreases strength due to increase in strength. Since it is in increased strength, that's why it's wrong. So correct option will be the third one. So hopefully I was clear. If any of you have doubt, please let me know. I can explain it again. Okay, if there is no doubt, then let's move to the next question. Please have a look on the question and try to answer in the polling section. Yes, polls are live. Please answer there.
Here actually both two are there.
Oh, sorry, it should be 3 and it should be 4. Yes, I have got the 3 responses and all of them are correct. Okay, let's quickly go through the question for the people who don't understand the question or they are finding difficulty to solve it. So what happens is that transformation hardening, we typically take the example of the steel, where we try to improve the property of the steel material by doing some transformation. And in steel, this transformation happens in its phase. Basically, if steel which we have earlier is present in the form of the perlite, then by doing heat treatment we try to improve its strength, and the martensitic transformation happens because of the heat treatment which we do on the perlite. Or quickly I can show with the some schematic or the process flow diagram. Like initially we have steel in the form of, let's say, perlite. What we do, we increase its temperature up to 727 degrees Celsius to form austenite, and we leave it for some time for soaking, and soaking or homogenization. So basically this is two-phase region perlite, and we are bringing to a single phase of austenite, at the by heating it to the temperature of 720 degrees Celsius, and then it leaving for some time for homogenization, and then we quickly cool it rapidly, or we call it quenching. And we do it by putting the heated material into the oil or water. So because of that, we quickly cool it. The austenite transforms into the martensite, and there is property of this martensite phase that it has very good strength. Or hardness, but same time it is brittle in the nature. So I hope all of you know, all of you understand the meaning of the brittle. Let's say I will explain this also from the stress strain diagram. Brittle means the material has less ductility, or it can be deformed plastically to very little extent. So brittle means ductility is low. Suppose we have material 1 and we have material 2. Here what happens, for a given stress value, the material fails at here, let's say strain value is it's 0.1, and here let's say strain value is 0.5. So since I told that the brittle material have less ductility, based on the stress strain diagram, can you tell which is more brittle, material 1 or material 2? You can write it in the chat box. Which one is the more brittle? I haven't received any response. Can you please write in the chat box? I am asking which material is more brittle, or which material have less ductility. Okay, yes, Narottam is correct, because we can see the material 1, it has less amount of permanent deformation or plastic deformation, because it has gone up to the strain value of 0.1, whereas the material 2 has large plastic deformation. So this material has, and this material 2 can be deformed more before its failure. So this is the point of failure for the material 2, and this is the point of failure for material 1. And toughness. Toughness is the term. It is defined as the here toughness. It is defined as the total energy absorbed before failure, before, let's say, fracture. And from the stress strain diagram, for material 1 this is the fracture point, for material 2 this is the fracture point, and area under stress strain diagram gives the total energy for absorbed during the process. Sorry, that was a disturbance. Yeah, now my slides are visible. Sorry for the disturbance. Okay, hopefully it's working for all of you. So I will, yes, I was telling that the area under stress strain diagram gives the energy for unit volume. Energy, basically this area gives the amount of energy absorbed during the plastic deformation for the given material for the unit volume. So that is the definition of toughness, the total energy absorbed before fracture. And from the graph it is clear that the material 2 has the larger area, and that's why it has higher toughness. And I told that martensite phase has martensite phase is brittle in nature. It has low ductility, and because of its low ductility it can't be deformed much plastically, and therefore the energy absorbed during the plastic deformation for this material will be less, and that's why toughness will be the less. Toughness decreases. So for the martensitic phase, let's see the what are the options are there. Toughness increases. No, toughness will go down. Ductility and strength both decreases. Although ductility decreases since it is brittle, but strength goes up. In fact, martensitic phase has very high strength. And let's see the third option. Ductility increases. It is wrong. Ductility should decrease. Let's see the last option. Toughness decreases. Yes, toughness decreases, and hardness increases. Yes, hardness as well as strength. Very good hardness and strength. So this will be the correct option. Toughness will go down and hardness will increase. So am I clear to all of you? If any of you have doubt, please let me know, or I shall move to the next question. Okay, it seems Yes, anyone of you
Uh,
doubt?
Sir, will you upload these videos on the Swayam portal?
Yes, yes. It it's already, you will find a link for the live
Because I
session.
joined late, sir, because I was coming from my duty. So,
Yeah, yeah, yeah. You, it will, all videos will be uploaded on the Swayam portal. You will find a link by saying the problem solving session. There you can
sir,
find.
only these problems based on the assignment or the else?
No, these are the only problem which I am discussing at each Friday, on each Friday from 6 to
Yeah.
so from 6 p.m. and onwards. These will be uploaded there for each week.
Only based on the assignment which is given on the assigned course.
Yes, yes, yes. So basically, these are the questions from the earlier assignments, which will which will help you to which will help you to solve this year questions. So you will find there the problem solving session. There you will find the links for the each week session. You can
Okay, sir.
browse and you can watch any of the session.
Okay, sir. Thank you.
Okay, okay. Whether my slides are still visible to all of you?
Yes, sir. Yes.
Because there is.
Yes, sir.
Okay, okay. Let's move to the next question. So question number 7. Yes. Yes, this is the question from the break-even analysis lecture. Please have a look and try to answer in the polling section. Yes, polls are live. You can give your answer there. Others, please give your responses in the polling section. Till now I have got 3 responses. If you are finding difficulty to understand the question, you can ask me as well. Okay, let's start discussing the question. But unfortunately none of you got the correct answer. Okay, let's discuss here. uh, Basically, break even analysis. uh, this is the process which is used for selecting a manufacturing process, and it is totally based on the what is the economy of the process, as well as the if we suppose we want to manufacture any component, then what we have to do. we have to spend a lot of money for different things, and we want to see whether the process is economical for my requirement or not. For that, we used to do break-even analysis, and there the cost or the expenditure which we are going to do for different things has been categorized into different category. One is the fixed cost, and another is the variable cost. So let's see by one example. Suppose uh, I want to open a plant for steel manufacturing. Then what are the things which I needed? First of all, I needed machineries. I I need some capital cost for, let's say, land, or let's say I have to buy some technology, which will be required to at the beginning of the establishing my plant. So fixed cost are the cost which are the one time investment. They uh, it is the fixed, or let's say it is the one time investment. But there are some investment which we have to do regularly, like labor, material, and all these costs will depend on the how much quantity I am going to manufacture. For let's say if we are going to produce a small number of quantity, then we will require less number of labors, and then we have to pay less. And if the quantity is small, then we have to buy less material, less raw material, and the cost of material will be total cost of material will be less. So these are called the variable cost. So variable cost is the uh, money or expenditure which depends on the quantity of the production. But fixed cost are uh, those expenditures which doesn't depend upon the how much quantity we are going to produce. Like if we have machinery or machine tool, then it will be the fixed. Suppose if we have furnace, then the furnace once we purchased, then we don't have to buy it again and again for each time production for. And it doesn't depends on the whether I am using the furnace for producing 10 components, or I am going to use the uh, produce 5 number of components. The cost of furnace is going to be the fixed. So that is the one time investment, and that is fixed cost. So let's see from the question. Direct labor, we know if we have to produce more number of quantity, then we have to hire more number of laborers to handle the material or to operate the machines. So this will be a this will be a variable cost because it depends upon the quantity of the production. And material. Yes, Neruttam, please tell. Please unmute yourself.
Actually, in the industry, we are considering the manpower,
Yes.
labor, which is a fixed cost. Because if you have an employee of 1,000, and this month you will produce 100 ton, next month maybe 200, or but you have a fixed cost which is manpower. So either you will produce or not produce, you have to pay the salary to them.
Yes, yes, yes. That is true. But here we are considering that for fixed amount of production. Like suppose that if I know my sale is 100 quantity per month, then I will have, let's say, 10 laborers. And suppose if I know that I have to produce 1000 quantity, then definitely I have to increase the number of laborers. So in that way, if you see the amount of requirement of labor, that will be directly depending upon the how much quantity we are going to manufacture. So in that way, the labor cost will be the variable cost. I think it answers your question.
Okay. Yes.
But yeah, you told that maybe next month my production will go down or something happens. So that can be a situation. But here we are assuming that the product we a priori we know the amount of components which we need. So based on that, how much labor I should hire, it directly depends upon the how much quantity I need to produce. So in that way, the direct labor cost will be the variable cost. Yes, you have. Am I clear or?
Yeah. Yeah. Okay.
Okay,
Thank you.
okay, welcome. Now let's come to the material. Yes, it is obvious that if we have to produce more quantity, then we have to buy more material, and it will also be a variable cost. And energy. Yes, energy cost will be directly proportional to the amount of production or the quantity of the production, because if we have to produce more, our machines will run for the longer time, they will consume more power, and we have to pay for that power. So energy cost will also be directly depending upon the amount or quantity which we are going to produce. So energy cost will also be a variable cost. So all three are here variable cost, and therefore the correct answer will be the variable cost. So I think I am clear. If any of you have doubt, please feel free to ask me. Okay, it looks like it's clear to everyone. So let's move to the next question. Yes, this question is again on the break-even analysis. So please take a little time to understand the question and keep your response in the polling section. polls are live. Read the question carefully and try to look at the options. Check which of them are correct. Yeah, it looks like uh, few of you are facing some difficulty to understand the question. Okay. Yeah, if question, all of you are able to understand the question. Okay. Yeah, I have got the 3 responses. Yes, 2 of you are correct. So let's discuss this question, and again please all of you again try to answer the question after the explanation. So for the break-even analysis, the total cost of 2 manufacturing processes 1 and 2 in an industry are shown below in the figure, which is this figure, and based on that we are given few options which we have to select which one is the correct. Here we are trying to compare the total cost of production for using 2 different processes. Let's say this one is for the process 1 and this one is for the process 2, and similar kind of diagram I also have drawn on the right hand side. Let's say the process 1 is for the metal forming process, and process 2 is the machining process. Just for the example, but we can take any number of process. We want to manufacture a component that can be manufactured using many processes: metal forming, machining, casting, or any other powder metallurgy. But we have to choose a process which should be the economical for us, so that we could get maximum profit out of each. So how we will do that? So that is done by the process called break-even analysis. So what here we have 2 processes, process 1 and process 2. What we will do, we will try to plot the variable cost, fixed cost and variable cost. Cost, these two we will try to plot the fixed cost and variable cost on this graph. What is this graph? X-axis shows the quantity and y-axis shows the cost required for particular quantity. So what I have done, we are taking, let me choose the ink color. Yes, here let's take the process number 1. First we will try to plot the fixed cost for process 1. Where it is, this is here. FC means fixed cost for option 1. As I told, fixed cost will be constant. Whatever the number of units we are going to produce, the fixed cost will not change. That's why this is the horizontal. So whatever the number of units we are going to produce, the fixed cost for the process 1 will be this. Similarly, fixed cost for process 2 is here. So both costs are, so from the graph we can see the fixed cost for process 2 is higher, whereas the fixed cost for process 1 is lower. But what about the variable cost? So let's plot the variable cost for here process 1 and variable cost for process 2 in the same graph. Here this line shows the variable cost for process 2. We know that the variable cost depend upon the number of units we are going to produce. That's why for the smaller number of production we have less variable cost, and for higher number of units of production we have higher cost. So that's how we have plotted the variable cost for the process 2, and similarly we have plotted the variable cost for process number 1. And we can see, since the slope for the variable cost of process 1 is higher than the slope of variable cost of process 2, that's why it is steeper. It means as we keep on increasing the production, the process 1 will become more costlier than the process 2. So now next what we will do, we will try to plot the total cost for the process 1 and process 2. So which is the sum of total cost is the sum of fixed cost plus variable cost. So that is here. This plot shows total cost for process 2. Here basically it is the sum of variable cost, this variable cost of process 2 and variable cost of process 1. So this graph shows the sum of these two, and similarly this line shows the variable cost for process total cost for process 1, which is the sum of this process as well as the sum this process. Now what we see, the total cost line intersect is this point. So what does it mean? It means that if we have, let's say this is the Q star, this is the point where the quantity is Q star. So if we want to produce a component if you want to produce the number of component, let's say Q star or below it, so here we have a process 1 which requires less cost, or it requires less expenditure, because the graph of total cost is below, for the process 1 is the below the graph of total cost of process 2. So if our required quantity is less than Q star, then process 1 will be the preferred process based on the economy. And similarly, if we see after the Q star, the total cost for the process second is lower than the total cost for the process 1. So if our required quantity is higher than the Q star, then our second process will be the economical. So this is the concept of, or the process of, break-even analysis. Now all of you can give your response again. You can edit your response in the polling section for this question. If you are clear, or if you have doubt, please ask me, so I will try to make you clear. Still I cannot see any more response. Okay, let's start looking at each options. Let's see what is the first option. It is the process 1 is preferable for units producing less than Q star. Yes, it is correct, since if you see this reason, the amount of quantity which is needed is less than the Q star, and since process 1 is more economical, it requires less cost to produce the component, so this is the correct option. And let's see the other options also. Process 2 is preferable for units producing less than Q star. No, since it requires since it is higher, it requires more cost to produce the component if the quantity is less than Q star, so it is not a correct option. The third option is the industry will always be in benefit irrespective of number of units produced. No, as we discussed, it depends upon the number of quantity which process is suitable for the production, so that is also a wrong option. What is the fourth option? The process 1 and 2 both are independent of units producing in the terms of benefit or the loss in the industry. No, it is wrong. Process 1 is economical if required number of quantity is less than Q star, and process 2 is economical if required number of quantity is greater than Q star. So I think I am clear. If any of you have doubt, please let me know. I will wait for your queries. Okay, since there are no queries, let's move to the next question. Read the question, and I will till then I will start the polling. Yes, polls are live. You can give your response there. Okay, yes, I have received the responses. So yeah, two of you are correct. Okay, let's discuss this for everyone. Question is, casting is more prone to defects. So we have process casting, and we have to see what are the whether the options which are given is correct with respect to defect in the casting. Okay, let's see the first one, the range of solidification temperature. So I have taken this directly from the lecture to explain everyone again. During in the casting process, we have molten metal. We try to put it into the mold of required shape, and we we leave it leave it for the solidification, and then we try to remove the mold and try to get the final product. And there is a process which is important, which is the solidification process. So this one is a typically graph of the solidification process for two different type of materials. This graph is between the temperature versus time, and this is the point where our material is in the liquid form, so the temperature is higher. And what happens when we pour the metal inside the mold, it will start the temperature will start decreasing, so it will keep on decreasing till a point when its molten phase become to transform into the solid, that is called the melting point. For the pure metal and eutectic metal system, so later on it will be explained in one of the lecture what is the eutectic system, what are the eutectoid system. So please just, it is for just for the information that these two metals have constant melting temperature. It means the whole material will get solidified at a constant temperature, so it will have a fixed melting point. So pure metal and eutectic metal system. But for the alloy system, the melting point is not the constant, so it happens, the melt basically solidification happens for a range of temperature. And because of this property, there are different kind of defects occur in the casting. Let's say for the first one, since it has this type of material system have a constant melting point, so molten, or suppose this is the mold and is inside it has molten material, so all material will solidify uniformly because they have constant melting temperature, and all material will solidify at the same temperature, and it will be more uniform. But what happened to this kind of system? Here this is the mold. Earlier we have metal, and this molten material will solidify for a range of temperature. So because of that, what will happen? The material which will come in the contact of the mold wall, that will starts cooling earlier. So all the material which are near this region, they will start solidifying first. So since the material near the wall starts solidifying earlier, so the what will happen, the pure material, or the, let's say, alloy, in alloy, one of the alloy component will start getting solidifying first, and other one will keep on dissolving in the molten material. And because of that the other alloying elements, they will come in between the molten metal, and solidification will keep on increasing from the walls towards the center. And because of that, the in the center it will solidify in the last, and it has the maximum alloying components, because the alloying material, they were not able to solidify in in the beginning of the solidification, so they kept on dissolving in the center position, and at last this region will have more alloying components. And therefore the composition of the solidified material is not uniform. It has more alloying components in the center, whereas near the walls of the mold it will be pure metal. So because of that, the composition is non-uniform. It is a defect. We want a component which have uniform composition throughout, but it doesn't happen because of the range of the solidification temperature. So yes, if we have range of solidification temperature, then it will have a casting defect. It is correct. Affinity to metal to atmospheric gases. Yes, it is right, because if we have molten material and atmospheric gases will dissolve inside it, and they will act as a impurity. So they will increase the impurity. It is not desirable. So if material have more affinity to the atmospheric gases, then it will also be prone to the casting defect. So it is also a correct option. And this one is difference in the solubility of gases in liquid and solid state. Yes, if it will happen, then in the molten state more solubility, but in solid state less solubility. Basic solubility of gas. So this is the very undesirable phenomena, since mostly the metals have higher solubility in the molten state, so lots of gases gets dissolved inside the molten material. But when solidification starts, then solubility of gas decreases inside the molten metal. The problem comes when these gases will not able to escape because of the poor permeability of the mold. Then what happens? Then they will entrapped as a they those gases will remain entrapped inside the solidified material as a porosity or the blowholes. So it happens, it is totally undesirable. We want a casting product which is free from pores, free from impurity, free from blowholes. It should be the uniform, but because of the difference in solubility, we get blowholes or the porosity. So difference in solubility will lead to the casting defect called blowhole and porosity. So this is also a correct option. Since all of these are correct, so fourth will be the correct option, that because all of above. So I think I have answered this question. So any of you have doubt, please ask me, or I shall move to the last question. So none of you have doubts, then let's move to the last question of the session. Okay, this is also related to the casting process. Please have a look and try to answer the question. Meanwhile I will create the polls.
The question not displayed, sir.
Yes, yes. Okay, I see. Yes, now it's visible.
Okay, okay.
Okay, okay. Sorry. Yes, I have created the polls. Please spend some time and try to give your responses in the polling section. Yes, I have received 3 responses. So others, you can also try for a minute, and then we will discuss. Okay. Uh, Unfortunately, none of you are correct this time. So let's discuss and let's see what is the correct option. Let's start discussing the terms one by one, and before that, try to understand what is being asked in the question. The question is, fluidity of material in casting process is affected by the properties. These are listed below. The let us first define what is the fluidity. It's the simple. It's ability of flowing of material to flow. So what happens in the casting? We uh, we try to pour the molten metal inside the mold, and molten metal tries to fill up the mold cavity. And suppose we have this kind of mold. Yes, this we have we have the sand mold, and this is the cavity region. I will show it by different color. This is the cavity, and we try to pour the molten material inside the mold cavity. So material, when we try to pour the molten material, our aim is to the material and the molten material should flow by itself, and it should reach the each and every corner of the cavity, and it will happen only if this molten material have good fluidity. And let's see, uh, these are the few physical uh, properties of the any material which are listed, and we'll try to see what are the effect of each property on the fluidity. Let's us first discuss the thermal conductivity. Thermal conductivity refers to the ability of the material to conduct or transfer the heat. Basically, how did we melted the material? Earlier we have some raw material in the solid form, we heated it, and then finally it melts to the liquid form, so which is shown here. Suppose if this molten material have high thermal conductivity, then what will happen? Then heat, if it is a high thermal conductivity, then he tries to escape from the material via the mode of conduction. So heat will try to come from the molten material, and it will try to go into the mold. And if heat will go away, what will happen? Then this molten material will it will start solidifying. It will no more remains in molten form, and if it will start the solidify, then it cannot flow. So if thermal conductivity of molten material will be higher, then heat will escape faster, and molten material will start solidifying quickly, and because of that its fluidity will become lower, and it will not fill the whole cavity. Therefore, thermal conductivity is the property on which the fluidity of the material depends. So this will be the correct option. Let's see for the second. The coefficient of thermal expansion, it is defined as, it describes how the size of an object changes with the change in temperature. So if we have a solid component, we try to heat it, then its size increases, and it happens because of the property called thermal expansion. But this property has nothing to do with the fluidity of the molten material. So this property will not be appropriate with respect to the fluidity of the material. It won't have effect on the fluidity. So coefficient of thermal expansion will not be a correct option. Let's see the third one, is specific heat. How it is defined? It is defined as the quantity of heat required to raise the temperature of 1 gram of substance by 1 degree Celsius. So suppose we have 1 gram of material and its temperature is 25 degrees Celsius. We try to increase it to 26 degrees Celsius. We have to give some heat, but different material will require different amount of heat to increase its temperature from 25 degrees Celsius to 26 degrees Celsius, or to increase its temperature by 1 degree Celsius. So if a material have high specific heat, then it will contain more amount of heat. Basically, we had 1 gram of material, and if we have to give larger amount of heat to increase its temperature by 1 degree Celsius, then what it means? It means 1 gram of material has higher, it contains higher heat energy. If we have another material which requires less amount of heat to increase its temperature by 1 degree Celsius, then it will contain less amount of heat energy. So if a material have high specific heat, then it will contain more heat energy. What it means? It means here, if this molten material have higher heat energy, higher specific heat, it has higher amount of energy, then it will take longer time to solidify. So if a material have high specific heat, it will contain large amount of heat energy, and it will take larger time to solidify. It means a material will remain in molten form for larger time. If it remains in the molten form for larger time, then it will have high fluidity for longer time. Therefore, high specific heat implies higher fluidity. Therefore, specific heat is the property which affects the fluidity. So this will also be a correct option. Let's see the last option. Melting point. Yes, it is very easy, all of you know that it is the temperature at which material starts melting. So if suppose that we have molten material, sorry, suppose we have molten material, here we have molten material, it has a melting point, and as far as the we are above the melting point, it will remain in the form of liquid, but as far as we go below the melting point, then it will solidify. But until and unless we are above the melting point, we don't have to care about the fluidity of the material. Basically, above the melting point, the material will be in the liquid form, and as far as it remains in the liquid form, its fluidity will be more or less same. So it just its melting point just defines the above which material will remain in liquid form, but above the melting point, whatever the temperature will be there, the material will remains in the liquid form, and it will have good fluidity. So fluidity is not a function of the melting point. Therefore, it will be not a correct option. So what are the correct options we have found? This first one and the third one. So okay, this option second. So this is the correct answer. Okay, so this is the answer for the last question. So if any of you have doubt, please ask me.
Thank you.
Okay, it looks like no one have doubts. Okay, if I am clear to all of the questions, then we can end the session here, and we will meet next week on the Friday at the same time with new sets of question based on the lectures which will be taught in the week 3. So all the best for all of you. Have a nice weekend. Okay, bye.
Okay.